We know that as we build will be more. Each time we are washed away, we bounce back to the shore. We know we lead the way, keeping odds at bay. To see the sunrise tomorrow, inspire the world to follow.
Okay, so in module number 5 of electric drive curriculum, today we will going to discuss effect of resistance on induction motor drive. Okay, so let's start lecture number 11, effect of rotor resistance on induction motor drive. And this is the objective of our this module. We already discussed several times, so you please go through at a glance through the objective. Okay, so let's start rotor resistance control. Now when we have studied three-phase induction motor, there we have discussed that the speed of the three-phase induction motor can be controlled by varying the rotor resistance, especially for slip ring induction motor, especially for slip ring induction motor, because in case of squirrel cage induction motor, the rotor circuit are shorted with end rings, so there is no provision of change the rotor resistance. So this is only applicable for wound rotor type induction motor or slip ring induction motor. Now we have know that this is the equation of torque, starting torque, 3 by omega s into this is my starting torque, and this is my maximum torque. Okay, so if we, and this is the slip at maximum torque, this is slip at max torque. So we have read this in our basic electrical as well as electrical machines. Now if we see the torque equation, and if I simplify this a little bit, so what we get that this is the ultimate torque equation. T is proportional to slip, and torque is inversely proportional to 1 by R. That we can conclude from the torque equation. So that if we can consider that the motor torque is constant, then the resistance is directly proportional to slip. Resistance is directly proportional to slip when torque is constant. So if we can change the resistance, we can change the slip, and if we can change the slip, we can change the speed of induction motor. Okay, we can change the speed of induction motor. So this is the diagram. So if we see here, this is my maximum torque, this is my maximum torque. Okay, and this torque is denoting the starting torque. This is also the starting torque, and this is for another torque speed characteristics. So there are three different torques versus speed, or torque versus slip characteristics. And if we see that this characteristics is basically for three different resistances, which are R23, R22, R21. Now R23 is greater than R22 and R22 is greater than R21. So if we see that as we increase the resistance from R21 to R22, from R22 to R23, the interesting fact is that my corresponding slip at which that maximum torque is occurring also changed. But keep one thing in mind, that the value of maximum torque remain unchanged. So although due to the change of resistance, corresponding slip has changed, because for constant torque we just talked that R is proportional to resistance is proportional to slip, but the value of maximum torque remain unchanged, and this is the typical load characteristics. So this is the intersection point with curve 1, curve 2 corresponding, and this is curve 3. So if we see here that in this direction speed is increasing from 0 to ns, so obviously the slip is increasing in this position. So for the change of resistance, as the resistance changed from smaller value to higher value, the maximum torque occur at a higher slip value. And if you check that in this method, the corresponding speed also decreases. So this is how, by changing that by changing the resistance we can change the slip, and correspondingly we can change the torque. Okay, and this is my torque versus speed characteristics. I have just shown this you to now, but it should be noted that we should keep in that mind, it should be noted that the speed variation by rotor resistance adjustment is very inefficient because of the additional power loss in the rotor when speed is reduced, because of the operation with high slip with high rotor resistance. So which I have just discussed now, that at constant torque R is proportional to S. So as the R value is increasing, the slip value at which the maximum torque occur increasing. So that is why it is mentioned that high slip with high rotor resistance, and as the slip increase we have seen that speed is also reducing. So there is a huge power loss. So that's why this is a very inefficient method. And this is basically used for cranes, hoist, excavator, any intermittent type of load. Okay, and depending on the rotor resistance, the rotor speed falls or increase. Okay, so we have discussed this, but the losses mainly take place in the external resistor. They do not hit the motor. So this is also we have to kept into our mind. Okay, now if you see, we know that P2, that is the power in rotor circuit. This is power in rotor circuit. This equals to 3I2 dash R2 dash by S. Okay, and what is my developed power or shaft power? This is equals to P2 minus 3I2 dash square R2 dash. We have learned this from the power flow diagram of induction motor. So if we simplify this, it will become 1 minus S into P2. So that means we are getting P0 by P2 equals to 1 minus S. So if you see that as the constant torque rotor is proportional to slip, so resistance is proportional to slip. So as the resistance is increasing, so slip is also increasing. Now if this slip is increasing, so this value is decreasing. So P0 is nothing but 1 minus S into P2. So as this value is decreasing at higher slip, results in a smaller proportion of power transferred to the rotor, which is converted to the shaft power. And obviously the difference of these two is the power lost in rotor. And we should keep in mind that it should dissipate adequately to avoid the rotor being heated up to high temperature. So this is also we have to keep in mind. Now this rotor resistance control method can be implemented in two ways. One is called the conventional method of variation of rotor resistance, which is done by inserting a variable rheostat in series with a 3-phase motor. Or in drum controller, resistance is varied by using rotary switch. So in drum controller by changing the rotary switch, we can change the resistance. Okay, now variable resistances can also be obtained by using contactors and resistor and series. That is what I have mentioned. High power application use a slip regulator. So this is also conventional method. This is also done by slip regulator, and this slip regulator is basically consist of 3 electrodes submerged in electrolytes. So 3 electrode which submerge in electrolyte, which is consisting of saline water. And this resistance is varied by changing the distance between electrode and the earth electrode. So this method speed control faced problem, and this was not economically viable. Okay, and the advantage of this method is that resistance can be changed steplessly. Resistance can be changed stepless. So this is the advantage. So what is the solution? So the solution in this problem, thyristor is used to switch the connected across external resistance and effective resistance is varied simultaneously. So this is basically called rotor resistance variation using chopper. So this is rotor resistance control using chopper, and this is the circuit. Okay, now if we see here, so this is the circuit. Okay, so this is the circuit and this is the waveform. Now the AC output voltage of the rotor is rectified by this diode rectifier, and mind it, this is a uncontrolled bridge rectifier. This is a uncontrolled bridge rectifier. This is an uncontrolled bridge rectifier. Okay, and this is fed to a parallel combination of fixed resistance R and a semiconductor switch realized by a transistor TR, which is used here. Now this effective value of resistance, across the terminal AB, that is the effective value is RAB. Okay, this varies by varying the duty cycle D, that is T on by total time T on by T. This is my duty cycle. So by varying the duty cycle, we can change the value of effective value of the resistance, and this LD inductor is used to reduce the ripple and discontinuity in the DC link current ID. So this is ripple elimination has been done. Now if we neglect the ripples, and from this waveform we can easily determine the RMS value of RID, which we have done in our basic electrical. Okay, so if we perform this 1 by root mean square, we know that 1 by T integration 0 to T, okay, I square dt under root. So we can, using this, we are getting IR equals to root over of 2/3 ID. Okay, so the resistance between A and B terminal will be 0. This will be 0 when the transistor is on. Transistor is on means this is shorted, so the resistance is 0, and it will be R when it is off. Simple logic. So what is my average value? RAB into 1 minus delta R. Here delta is used as duty cycle instead of D. Okay, so it can be write down as well 1 minus D R as well. Okay, so this is the duty ratio. So therefore the total resistance is varied from RR to 0.5 1 minus del into R, as del is varies from 1 to 0. You put the value of D here from 1 to 0 to 1, and corresponding we will get the value of R. So which is consumption of power, electric power consumption in RAB per phase, 3 phase, so PAB by 3. So that is 0.5 into 1 minus del IR square, IR square. Okay. So this is the power consumption. Okay. Now this is a closed loop speed control scheme. This is a closed loop speed control scheme with inner current control loop. Here we have used a inner current control loop. So this is the inner current control loop. Inner current control loop. Now the rotor current IR and therefore ID has a constant value at the maximum torque point, both in plugging as well as motoring operation. This to IR and ID has a constant value. If the current limiter is made to saturate at this current, the drive will accelerate and deaccelerate at the maximum torque, giving very fast transient response. Okay, and for plugging arrangement will have to made for reversal of phase sequence. So if we change the phase sequence from motoring operation, we can convert into a plugging operation. So this current limiter is made to saturate at this current. So setting is such a done in this constant current it made saturate, and which results in the drive to accelerate and deaccelerate and maximum torque. Now compared to conventional rotor resistance control, static rotor resistance control has several advantages. Static resistance control means using that chopper circuit. This is known as static resistance control, which is that smooth and stepless control. So smooth and stepless control. So let me wait. Here. So the advantage is smooth and stepless control, fast response, less maintenance, compact size, simple closed loop control, and rotor resistance remain balanced between the three phases for all operating point. Okay, so this is all about rotor resistance control. So we have covered this. This is the static rotor resistance control. Okay, this is the another picture which we have shown this duty cycle and corresponding value of resistance and the voltage. So from here we can get this value of R, okay, which we have discussed. Okay, and this is also we have discussed. This is the closed loop speed control with static rotor resistance control. Okay, so this is all about rotor resistance control of induction motor drive, and in our next class we will discuss the slip power recovery scheme. Okay, so these are the reference. You follow this GK Dubey book. Okay, Ned Mohan, PK Bose. These are the few good books. PS Bhimra, and also you can consult Google, Wikipedia. Slide share, scribed. So these are the few online resources. These are the few online resources. Okay, so this is all about today's class. Thank you.